So today we are going to explain the theorem. This is called to verify the network theorems. So today we perform the practical on Thevenin's theorem and Norton's theorem. But before going to discuss the practical, first of all you have to clear with the theoretical concepts. That's why there are certain steps to solve the circuit on network theorems. So first of all we will discuss what are the circuits, what is the given problem, and then later on we will understand how to perform the practical. So next we will perform the practical on the breadboard. But first of all we will discuss what is mean by the network theorems. So the basic aim of the network theorem is any circuit is given. So circuit means electrical circuit. This electrical circuit, there are number of resistors and capacitors are connected. So basically we are performing this experiment for DC circuits. That's why in all the circuits we are using only the resistors and the necessary power supplies and meters are there. So this is a circuit for DC network. So these circuits includes the resistors and battery or voltage supplies. So what is the need of network theorem, we will first of all discuss. The need of network theorem is to calculate the unknown parameter. So whatever is the unknown parameter, so basically the unknown parameters are voltage and current. Voltage flowing through the voltage drop across the resistors and current flowing through the resistors we are calculating through the network theorems. So today we are dealing with both the theorems. This is called as the first is the Thevenin's theorem and second one is the Norton's theorem. So that first of all look at to this circuit diagram. One circuit diagram is given and the aim is to calculate the current flowing through RL. So this is the RL. RL is a value of 1 kilo ohm resistors and we want to calculate the value of IL. So to calculate the value of IL we are using the network theorems. And in that network theorem, in this practical, in experiment number 1 and experiment number 2, we are going to use the Thevenin's theorem and Norton's theorem. There are again number of techniques to calculate the value of IL. There are number of theorems are available. Again, max power theorem is there. Again, we also use the KVL, KCL. But in this practical, basically we are focusing on the Thevenin's and Norton's. So that's why we are calculating the current flowing through RL by using the Thevenin's theorem. So if I want to apply the Thevenin's theorem, there are some certain steps we have to follow, and these steps are first of all we will explain. So the step number 1 is first thing we are calculate the VTH. So what is mean by the VTH? VTH is simply a Thevenin's equivalent voltage. So first of all we are calculate the Thevenin's equivalent voltage. So to calculate the Thevenin's equivalent, suppose the circuit is given and I want to calculate the current flowing through this 1K resistor. So we have to first just remove this 1K branch and call this terminal as a and B. And the voltage across between A and B is called as a VAB, and this VAB is equal to the Thevenin's equivalent voltage. Remaining circuit is same. The only thing is you have to remove the branch through which we want to calculate the voltage or current. And our aim is to calculate the IL. That's why we are just remove this branch and calculate the VTH across the terminal AB. So if we carefully observe the diagram, the voltage across VAB is simply the voltage drop across this R3 resistance. So first of all we want to calculate the current flowing through this R3 because we know the Ohm's law. V is equal to IR and I is unknown here. R is already known to us. The R is 330 ohm and the VTH or VAB is the voltage drop across this R3. So that's why first of all we are calculating this I. So this I is very simple. As per the KVL or as per the Ohm's law, I is V upon R. So V and R means what? R1 and R3 are connected in series. It is not 2. This is R3. This is R1 plus R3. So that's why R1 plus R3. This is 330 plus 330 and the voltage is 10. So this is total calculation. I is equal to 15 milliampere. So what is this I? This I is current flowing through this loop. and in the loop means in the circuit current is always remains same. So the current flowing through this R3 is also called as a 15 milliampere. So the next step is to calculate the VTH, and VTH is the voltage drop across R3. So that's why R3 into I. This is again as per the Ohm's law. V is equal to IR. The I is current flowing through this R3 resistor, and R3 is already given. So just 15 milliampere into 330 ohm. So VTH we will get the 5 volt. So the first parameter we achieve here as per the Thevenin's theorem. This is VTH, Thevenin's equivalent voltage. So we will just move to the next step. The step number 2. Calculate the RTH. What is mean by RTH? RTH is again a Thevenin's equivalent resistance. As we already discussed Thevenin's equivalent voltage, as we already calculate the RTH, Thevenin's equivalent resistance, but what exactly the meaning of this is that this is the equivalent. Suppose in my circuit number of voltage source are there, so we have to calculate the equivalent of it, and this is called as a Thevenin's equivalent voltage. So in this our case only one voltage source is connected, that's why we are calculating the VTH. In this again there are 1, 2 and 3 resistors are connected in my circuit. So the aim of the Thevenin's theorem is calculate the equivalent of that resistance. So as we observe this circuit, so the thing is that while we are calculating the RTH, if the voltage source is present in your circuit, this is our main circuit, here it is the voltage source is present, so this voltage source is replaced by the short circuit. If here it is the current source, it is replaced by the open circuit. If it is a voltage source, it is just removed and put here it is the short circuit. If it is a current source, we just replace it and place it an open circuit. So these all are the steps to calculate the RTH. So in our circuit there is a voltage source, that's why we just remove the voltage source and short the terminal. So if we just short the terminal, this is the equivalent circuit, and again the resistance across A and B terminal, this is called as RTH. This is the Thevenin's equivalent resistance. So as we just observe the circuit, this R1 and R3 is in parallel with the series of R2. So suppose we are just calculating this, what we get 495 ohm. This is the value of RTH. So we calculate the RTH, we calculate the VTH. Next we draw the Thevenin's and Norton's equivalent theorem. First circuit. First of all we will draw the Thevenin's equivalent. So Thevenin's equivalent circuit is very simple. As we already calculated the VTH, as we already calculate the RTH. So VTH in series with the RTH, and A and B terminals remains same. So VTH value is 5 volt, RTH value is 495 ohm. So what is this? This is called as a Thevenin's equivalent circuit. Suppose I want to calculate the Norton equivalent circuit. So this is again a very simple steps. What exactly the thing? This is the Norton equivalent circuit. As we observe, what the thing is that the voltage source is just converted into the current source and connecting the resistors in parallel with the parallel with the current source according to the basic rules. So what we get, VTH is equal to 5 volt, RTH is equal to 495, and if we are converting into the Norton theorem, so IN we get 10 milliampere and RTH is same. Simple. This I, how we are calculating this I is again V upon R. V upon R means VTH upon RTH, and simple we get the 10 milliampere, and this is the RTH is connected. This is 495 ohm. So what we get basically, this is the Thevenin's equivalent voltage and Norton equivalent voltage. So up till now we finish with the 80%, and the last part to discuss is to calculate the IN, and this is actually the basic aim. That's why we are applying the network theorems. So to calculate the IN, simple circuit, VTH is there, RTH there. So we already have the Thevenin's equivalent voltage, and here it is the A and B terminal. So between this A and B terminal we are attaching this RL 1 kilo ohm, whatever is the branch, to calculate the unknown resistance or unknown current or unknown voltage. At the last we attach this branch to the Thevenin's equivalent circuit, and simple, this is a simple thing. We are calculating the IL. IL is the current flowing, this is IL. So IL is equal to VTH. Again Ohm's law, I is equal to V upon R. So V is the VTH and R means RTH plus RL. So if just put all the values, so IL is equal to 3.3 milliampere. So this is all about the Thevenin's and equivalent voltage, but this is all steps are related to the theoretical calculations. So later on we will discuss what is the practical value or practical process. So as up till now we already discussed what is the theoretical calculation, and right now we will perform the practical. So to do just perform the practical, we require the power supply, we require the breadboard, and there are 3 resistors we are using in this circuit. This is 330 ohm, and these all are the connecting wires. And the important thing is we need the multimeter to measure the values. So the first task is to calculate the VTH. So as to calculate the VTH, here it is the simple circuit. In that circuit we are connecting the resistors as per the circuit diagram. This is as per the circuit diagram, and we are just connecting the power supply. So we are connecting the power supply here. And switch on the power. As we switch on the power, this is set at the 10 volt. So we provide the 10 volt, and just across the A and B terminal we are calculating the VTH. So we are getting the value 5.18 volt. This is the practical value of VTH. In theoretical we already have the value of VTH is equal to 5 volt. It's a very simple experiment. What the thing is, this is a simple circuit. In that we remove the 1 kilo ohm resistance. This is the RL. This is the unknown parameter. That's why we just remove this branch and just calculate the voltage across A and B terminal, and this is called as VTH. So VTH is completed. So second step is to calculate the RTH. So as we observe the circuit, this is a resistor R1, R3, and this is R2. So simply we are just short R1 and R3 here. This is shorting the R1 and R3 because we are connecting the voltage source here. If voltage source is there, we are putting it in short. And across this A and B terminal, we are calculating the value of RTH. So as we observe the value is 0.488 kilo ohm. So this is approximately 488 ohm. So 488 ohm, this is the practical value of RTH. As we already calculated in theoretical, 495 ohm.